All right, Dr. Ron England here with the database design using normalization. Well, this is another lecture on design. It's module 11. And what we're going to talk about is some of the practicalities of design. So there's a few things we need to talk about first. One is you kind of need to be able to look at the structure of a table. Now, there's a couple of statements in SQL that will be very, very useful. Most of the databases you're going to be working with will probably have lots of records. And you're going to need to look at those records and figure out what to do. All right, so select count star from table, or select star from table, or better yet, select top, let's say 100 from table. I usually do 50 or 10. Allows you to run a query and look at the table itself. And not just the table structure, because it's going to show you that. It's going to show you some of the data, because the data is actually important when you're looking at the structure of an existing table. Those statements are the useful beginning point for doing that. Now, when you look at the tables that you're assessing for design, you're going to look at functional dependencies, and there's some other things that we're going to look at, like multi-valued dependencies. Also the key structure, what foreign keys do exist, what primary keys exist. And here is a biggie. Interviewing data users or data input, okay? Because that is the number one piece of making the design, is what data do you need to store and how is that data going to be used? Okay, let me repeat that. What data needs to be stored and how is that data going to be used? Those affect your design more than anything else that you're going to do. Now, as you're going through and doing this, you also want to find out some of the business rules associated with that data, which normally translate into referential integrity constraints or other types of data constraints too, but referential integrity constraints are one of them. Those are rules, business rules, that need to be put into the database as enforceable rules. Now, I'm going to give you some examples that are really, really simplistic, but it's what we've got to work with. Here's one of the examples that we had here, and by looking at this data, you can say, some SKU numbers, some descriptions that go with the SKU numbers. Okay, that looks like a one-to-one. Then each of these things depends, they go to a department. Those SKUs of the that begin with 1 seem to all be water sports. The ones that begin with 2 or 3, the 2s seem to be camping, and the 3s seem to be climbing, and they have buyers in each of those. And we've also got, from the buyers, we can say, well, Cindy Lowe goes with camping, Jerry Martin goes with climbing, Nancy goes with water sports. Okay, so just looking at that data gives us some information about the structure of that data. So you want to get this, and this is an existing database. You'd say, oh, I'm going to look at what's in the table. I need to come up with some designs, or I'm going to look at what data I have. Now, in the case, this might also be in a spreadsheet. And oftentimes, you'll build databases by import directly from a spreadsheet. If you take my next class, COP4708, every single assignment, I give you data in some format, and you've got to figure out how to get it into the database. Why? Because you do that a lot, and you need to practice it over and over and over again. But good news is you get good at it. Now, in this case, you've got that set of data there. You've got basically what looks like to be a foreign key constraint, because you need to have that buyer that goes in the buyer table that goes with the SKU data table. All right, well, pretty simple example, but what can you do to see? We've got what? We can count them here. I didn't do a count star, but you got 1, 2, 3, 4, 5, 6, 7, 8. You got 8 pieces of data here in one table and 4 in another. What if there were 500,000 of them? Well, this might prove very, very useful to you, these different queries that are here to look at some of the data, but it doesn't give you all the situation that occurs here. So what are some things that you can do to check these things? What are some of the queries that you can look at? Well, here's a query that will actually work that you can do, and this is good to understand the well, actually the SQL structure here. If you look at this query, select buyer from SKU data where buyer not in, and then notice, boosh, you've got a parentheses and another query. So what you're really looking to do is say, oh, do we have any buyers that are not in that other table? Because that's what we've got here. That could be a problem. You could have some violation of foreign key constraints. Also, one of the things to look at is, hey, are some of these things declared null? I mean, a foreign key in a table does not have to be a not null. You can have null foreign keys. You can have pointers that say, okay, well, I don't actually have a value here that would be pointing back to the primary key of another table. That is allowable. I know that was a misconception that some people had, because sometimes you'd say, oh, well, here's my business rule. It either has to point, you have to have a row that points, or I'm sorry, a column that points to this table, or a column that points to that table, but not both. Well, both of those are indicating a foreign key to two different tables, but you might not have both at the same time. You might have one or the other. Ha! In that situation, you're saying, well, it's a foreign key from this column to that primary key of that other table, but it might be null. It's okay. But if it does have a value, that value must exist in that other table. That is a rule of the foreign key. All right, so we've got some types of databases that we're looking at. And these are, when I say types of databases, this is you saying this is how this database is going to be used. You don't go, I'm going to declare updatable database. But an updatable database is a thing. Okay, that's a database that you can update. Okay, now if you're dealing with databases that are read-only databases, that's another type that we actually have. They can have totally different designs. So updatable databases really just say what they are. They're databases where there's constant dynamic change and flow of the data. And for the most part, and I really do mean for the most part, they're going to be in BCNF. They're going to be close to BCNF. There's some exceptions to that. Because when you're in BCNF, you don't really have duplication of any of the columns in multiple tables. That's kind of the point of BCNF. Yeah, well, maybe not. And we're going to give an example of that. That's going to kind of make sense. So when you're designing updatable databases, you know that the big issue with the types of databases and putting them into BCNF is that you want to eliminate the anomalies of modifying data, where if you've got a data in one table and the same field sitting in another table, when you change one, the other one's got the old value in it. It saves some space. Big deal. Space is cheap. Unless you're talking about massive video files, you're not going to have an issue there. But it keeps that data integrity, especially that thing about having duplicates of the same piece of data in multiple tables. And by having those foreign key constraints pointing back, here's the primary key of this table, which is a foreign key in this table, you can't change it. Okay, that is a constraint violation, and the database will stop you from doing it. Now, here's the problem, and this is why we're going to look at not always following this format. When you've got all these tables in BCNF, you're probably going to want data from multiple tables in a single query. And when you have that, you're going to have to join those tables when you actually do a query. Okay, and what does this do? One is it makes the queries more complicated, but the other thing that it does is it slows things down, because when the database executes that query, it's going to have to join those tables together. And by joining those tables together to form a single table, that takes time and work. Now, there's a lot of optimization schemes, and yep, again, I'm pointing to COP 4709, 4709. Oh, wait, this is interesting. I'm actually reversed. Anyway, the camera, oh yeah, my door is backwards too. Okay, anyway, we are actually going to look at how to optimize the database. You can look at that right now. I don't think the Oracle tool that you've got access to right now has the major optimization tools built in, but when you get into COP 4709 and you're using SQL Server, you'll use SSMS, which actually has built-in optimization tools, and you can actually look at the optimization pathways, which you'll find, wow, that's kind of cool that you can see every step that goes on in a query and how long it took to do it with the data that you have. Okay. But those joins can slow you down. Okay, that is one of the things that happens. So a non-normalized table like this table right here, it's you know, you got repair mixed in with items. Okay, the same item is going to be repaired multiple times, but guess what? You can look at the table going, that drill press is showing up over and over again. Every time it gets repaired, all the information about the acquisition cost and the item number of that drill press is showing up in the next row. It's duplicated. Remember I said you want to avoid data duplication. If at all possible, you want to avoid it. And so we're going to try to avoid it. All right, so we normalize it. We take the repair, bring it out from the item, and voila, they are now normalized. Okay, that's standard, good old BCNF based design. Okay, you don't have that repetition there. You go ahead and have a foreign key that runs over to a primary key for each of the. So I mean, it's not hard to. This is pretty straightforward stuff. I would, by the way, in the item table, the second table where you're actually talking about the repairs, I'd move that repair number over one to the left and bring that item number over one to the right, because you kind of like to have the key, whether it's a surrogate key or non-surrogate key, you kind of like to have that key in the first column. You don't have to, but it does make your life easier because that's usually the place you're going to look for it. And I find that if you put things in places where you're going to look for them, you're more likely to find them. If you put them in places where you're not going to look for them, well, guess what? You can spend an hour looking for your keys. Put your car keys in the same place every single time, and you'll never spend time looking for your car keys. Now, what if we wanted to take data and move it over? Okay, here's a simple, straightforward pattern. Not hard to do at all. But you can insert into a table from a query from another table. Yeah. Now, this is only one specific pattern for this specific example. And this example is trivial. Okay. Because you got one table being put into two tables. That's pretty easy to do. And you know what? It happens. You're going to find situations where, oh, I need to convert this into two tables, put it in BCNF, and straightforward. But more than likely, it's going to be a little bit more complex. What do you do when you're looking at that? Well, you know what? There's a lot. I cannot teach you all SQL. There's a lot to SQL. Okay? But there's also a lot of great references and examples for the specific situations that you'll deal with. Same thing when I teach stored procedures. I'll give you the basics of how a stored procedure works, but you know what? It's like writing computer code. I'm not going to teach you every piece of computer code that you can possibly do. I'm going to teach you what commands you've got available to you, and you put them into the pattern that you need. So, knowledge, insert into a table from a query from another table, or a query from multiple tables, because queries can have multiple tables in them. Okay, and you can also specify specifically where you want these to go, which I did not do in here, but it's using the same column names anyway. Now, when do you not use BCNF? Okay, good example and my favorite example, and just use this as a guide to the example that you can say, you know what, this isn't in BCNF, but it's like the zip code example. And most people that work with data are going to go, yeah, I get it. The zip code example. Zip code will often show up in multiple tables repetitively. Or even possibly repetitively in the same table, which makes no sense, but you know, it is what it is. I have seen that happen. But it shows up. You don't need to normalize zip code into its own table. You don't. Okay. Guess what? It's a great example of when you can violate BCNF. Okay. You're not likely, and you know, it's right here. Zip codes don't change. They're, you know, they're pretty easy to catch. It's a 5-digit number. You can reference them against a table of allowable zip codes. It's not that hard to do with those. And there's plenty of examples like the zip code. Yeah. Now, multi-value dependencies. This is one of those things that you kind of have to make a decision. Don't separate tables, separate them. But so what do you, and this is a design decision. Now, let's say, I'm going to have some examples of this, but let's just say I've got 2 phone numbers. However, in my table, I have only a column for 1 phone number. But what could I do? Well, I could break my phone number out into a phone number table, and then I could have separate rows for me. There's my foreign key constraint, and my cell phone one, or maybe my office phone, multiple phone numbers, or I could have 2 phone number columns in the same table. One for each. Now, here's the problem. I got 2. You might have 3. Somebody might have 4. Where do you make that decision? If you have a separate phone number table, you can have as many phone numbers for an individual as you want. Not a problem. If you build it into columns in the existing table, you're going to have to make a decision. Is there 1? Is there 2? Is there 3? Are we going to call it phone 1, phone 2, phone 3? Are we going to keep track of maybe cell phone and work phone and home phone? Decisions, and those are design decisions. And how do you make those design decisions? Well, you do it based on how the data is going to be used. Because if you break those phone numbers out into their separate table, now anytime you want to put a phone number with a name, you're going to have to join those 2 tables. If you keep them in the same table, okay, and put 3 columns for phone number, well, you're not going to have to do a join, but you're going to be limited to the number that you put in there. So, that said, let's talk about read-only databases. And this is the place where you get to defy the good old BCNF rules. So read-only databases are databases where you pump a bunch of data into them and you use them for queries. These are query-based applications. You use them for generating reports, and they're also very useful for doing data analysis, AI analysis, and data mining. They don't go, now, do they get updated? Yes. But the way an update works is they get populated, boom, everything goes into that table, those tables all at one time from wherever they're coming from. Okay? They're not databases that are live in the sense that they go back and forth with data constantly being updated and modified. You dump the data into these databases and they exist there. At some point in the future, you may say it's time to erase all the data in the database, re-update it because there's new data that we got to deal with. Those are read-only databases. These are very common, very useful. Now, when you're talking about those types of databases, however, you don't necessarily want them to be fully normalized. They're stored in non-normalized tables. Now, how do you make a decision in read-only databases? What level of normalization do you want in those in the database? So let's say we've got these normalized tables, three of them. Okay, you can see that you've got these, club, club with the cost, student with that, and a payment that goes with the other piece. Okay, so now this would make a query where you'd have to put together a student to a club to an amount paid, and then check to see if they've met the cost of the club, would require 3 table joins, no less than 3. Because you'd have to say, okay, student Jones did not pay for his scuba, which would be $400. Okay, you can look at that. Student Jones did not pay, amount paid 0, for his scuba, and the club relationship is that the scuba cost is $400. Student Jones, however, did pay for his skiing because he's paid $550 and he's paid the entire cost of that. Okay, that's how those tables are related. May not be obvious right at first glance, but you can kind of still tell with it now. Now, what if you wanted to just say, hey, I want to quickly and dirty find out if the student has paid his cost for those things? Well, I can denormalize those tables by putting them all together. This is the type of query. This is the query right here that you would do. Notice that there's 2 joins. Remember that I said that you've got 3 tables. 3 tables requires a join of the primary table, payment data, with the other tables, student and club. And the joins are on the student ID and the club name. There we go. And when you're done, you get this other table. This is really easy to tell if student Jones has paid his scuba cost. Jones, club scuba, cost $400, amount paid 0. However, Chow paid for his scuba because he's paid $400 and $400. Okay, that was denormalizing that table. Now, anytime that you want to actually make that to see if somebody has paid for something, the query that has to execute would be this query or something like this query. Whereas if you stored this information in a separate table that has all of this together, maybe a read-only table, this is what you'd have. Okay, and this is really easy query because you could just take, okay, and you can do this. You can take the difference between amount paid and cost. And then that would tell you very quickly whether they've made those payments. So you've got the big deal about this, and I did put way too much information into this one here. You're going to have the same data showing up in a read-only database multiple places, because typically what you'll do is you'll have it targeted to the types of queries that you're going to run. And the queries are going to include duplicate information. You're going to want to know probably every single time, maybe the address for every kind of query that you do, which means that you're probably going to have the address in the table that you're querying each time. But remember, you're populating those tables from a common source. They're not getting out of sync. You're not going to go, oh, God, look, the address in this query for this person is coming out different from the address in this query, because you populated them from a common set of tables that was typically going to be a normalized version of the table, which we often refer to as the live. If you're going to be running any type of complex data analysis. Let's say we want to figure out what sales patterns are going on with different cities, states, and zip codes. Well, you're going to take that data from the live database, put it into a read-only table, probably have a specific table for each of the different types of things that you're analyzing. It's all going to be duplicated. Okay? Now, from this, you can see all the pieces that we put that customize it. Each of those tables has a specific thing that you want from it. Okay? Purchasing people want to know the information about the vendors and all that. The users want to know that the usage is we want to know how many of you sold. The web people want to know information like pictures and descriptions. And the inventory people want to know what's its SKU, how many have you got in stock. Those are customized tables. How do you get this? You interview the users and figure out how the data is going to be used. And you make decisions based on it from there, from that information. And you also make the decision of how much is going to be read-only and how much is going to be, because it can be the same database with just tables for those specific things. Read-only tables only. So it doesn't even have to be a read-only database. It can be read-only tables within a database. And as you can see, look what we've got here. You've got multi-value, multi-column. Okay, go back and say, oh, vendor contact 1, vendor contact 2. That's multiple values in the same table, in the same one there. And you've got multiple candidate. I mean, you got all sorts of stuff in here. Okay, inconsistency in the values because you got things that are repeated. You got potential for missing values, and I remember this design. Descriptions, but one of the ones that you deal with all the time, I'm going to go back down again, the general purpose remark column, which often you use to put remarks to yourself about what you missed in the other ones. So the multi-value, multi-column problem, there it is. The employees got auto license number 1, auto license number 2, auto license number 3, multi-value dependency. Do you use a separate table? Do you not use a separate table? You can definitely put those license numbers in a separate table and then foreign key them back to the employee. Depending upon how you're going to use the database, depending upon whether you know that there's always going to be 3, depending upon whether you know that there's only specifically 3 that we need to keep track of, well, make that decision part of what you do. If you know there's always going to be 3, and that you're going to run queries that need to know all 3 of those on a regular basis, okay, I'm not putting it in a separate table. I'm going to follow the business rules, even though it looks like we're, because of the multi-value. You got multiple values, multiple columns. Inconsistency. Oh, my favorite. This is something that happens all the time. This is where people that consult make a lot of money cleaning data. So, is corn large can the same as can corn large or large can corn? Or coffee and coffee and coffee? Okay. It's, you want, let's say you're doing an analysis, you want to know how many people bought coffee. Or how much coffee you sold. And coffee appears in the database under all 3 of these different spellings. Now you've got to do where item equals coffee, spelled each of the 3 ways. And you've got to say or coffee or coffee. Or you fix it. And there's easy ways to fix it if you know that these inconsistencies occur. Here's the fun. Finding those inconsistencies and making the decision, is it truly an inconsistency, or is corn, a large can, different from a large can corn? Those are things that data people do. So, some queries that can help you out with figuring these out. Group by is a great modifier for a select. Okay. You find these by running the right queries. The other one, way I like it is the like. I didn't go in to the like. The other one that I use quite a bit is the full text index, and then look for common matches to the way things are said. There's another, and that gets way beyond what we're doing in this class, but I guess just suffice it to say there's more ways to do this. The easiest is the group by. Missing values are another one that you've got to work with. Missing or null. And by the way, missing is not null. A missing value and a null value are not the same thing. A missing value can have the value null in a database, but a missing value doesn't mean that it's null. Null often actually takes a specific meaning. So an empty string in a database is not the value null. Okay? And the actual meaning of a missing value mentally and a null value can be different. Okay? So, in the situations of dealing with null values, there are appropriate places to have that the values should be null. If you just don't have it, it's null. But null values, when you haven't entered any data, the data record is null. Okay? So, example, date of last childbirth makes no sense if the person that you're looking at is male. Okay? It also might, and that has a specific meaning. Okay? It's inappropriate. It just doesn't exist because it makes no sense. Okay? It would be appropriate for a female in a database, but it may be null because we don't know what that date was, which is different from it being inappropriate. So null now takes on two meanings, not one meaning, but two. Okay? See what I'm saying with this? That when you're doing queries, you want to know what a value means in the data. So for when you do a query where you say date of last childbirth equals null, and you're going to say, well, that's going to tell us how many women we don't know the date of last childbirth, and you got a bunch of men in there with it null, it's not going to give you what you think it's going to give you. Okay? Dealing with null. So what you really want to do is in the design, if it's unknown, let's make it unknown, not make it null. Okay? We can easily check for nulls. Is null? Easy to do. So you can look at it and go, oh, let's look at these. And I typically don't do the count star. I'll just do star. And I'll look at it and go, well, these make sense as nulls. These don't make sense as nulls. Why are we using null there? Maybe we need to change some of these to something else. Maybe we need to use a coded field to say, these are what these values mean. The general purpose remarks column. Dun, dun, dun. I think I'm going to end on this one here since I'm getting kind of lengthy. Yeah, we have these. And with full text indexing, I mean, the terrible thing about the general purpose remarks column, and they're usually varchar maxes, you don't know what, I mean, you don't consistently know what's going to be in that column. It doesn't make it searchable. It can be a lot of things. Now, you can have rules which are interface rules. This is me actually going back to the programmers to say, only put stuff into the general purpose remarks column if the data is in XML or JSON format, which allows us to do internal queries of that field. Yeah. Or you can full text index that column, and that allows you to do some very enhanced queries on the general remarks column. These are new additions into database programming, though, database capabilities. If you don't have to use it, don't. But I'm not going to say don't do it, because I will often put a general purpose remarks column into a database. I'll put a full text index on that, and now it's completely searchable on fields that are within the text of those. But also realize that there can be problems. All right, I think I'm going to end it with that one. I think that's far enough to go with this. I think I've given you a lot of things to think about with design, but and here's the reality of this. This is why designing databases for specific applications actually is an interesting and intellectually stimulating field. If it was all cut and dried, it wouldn't be anywhere near as interesting. So these are design decisions, and these decisions, you can't say it's right, you can't say it's wrong. I can say that was a bad decision. I mean, y'all would have done it this way. But then there's always the argument that, well, am I right, or is the person who designed it right? Okay. Really, it's all comes down to the usability of what you've designed. But you've got the tools. You know what BCNF is. You know how to deal with referential integrity constraints. You know how to look for these different things that occur. You now have seen read-only and updatable databases and have a difference to these things, and know how that database is going to be used is important. I'm going to stop it there, and I hope that you really enjoyed this one, because this is where we really get into the interesting part of doing this. And then we'll get into some interesting queries too. Later.